In talking about a chi-squared analysis, I think the PowerPoint here makes it relatively clear. This is under the notes section. I'll also give you lots of practice questions and a quiz on it. The idea behind chi-squared analysis is to compare observed data to expected data. So you're really going to test a hypothesis using chi-squared analysis. So let's suppose that I say I bet you $1,000 that every time I flip a coin, I can get it to predict whether it's going to be heads or tails. And so let's say you say, okay, $1,000. The first time I say heads and I flip the coin and it lands on heads. Okay, so I got lucky. Second time I say it's going to be heads, flip the coin and it's heads. The third, fourth, fifth, and so on. Eventually you're going to have to suspect I'm using a two-headed coin. So when do you stop saying, okay, he's just getting lucky, and when can you use evidence to accuse me of cheating you? Well, you can use chi-squared analysis to do this. We're going to start with what's called the null hypothesis. The null hypothesis is something that was discussed in the experimental design unit. So if you need to go back there and review that, you can. For a chi-squared analysis, we're always going to start with the assumption or null hypothesis that the results are due to random chance, not due to any experimental conditions. So it's easier to disprove something than to prove it, because to prove it, you've got to be able to do it an infinite number of times in an infinite number of scenarios. But to disprove it, you can say, well, it didn't work in this case, therefore it's disproven. So the goal for chi-squared analysis is to disprove the null hypothesis, thus supporting your alternative hypothesis. So let's take a look at how this is done. We're comparing our observed results to our expected results, and our null hypothesis is that it's purely due to chance. The alternative hypothesis would be that it's not due to chance, that there's a two-headed coin involved here. So you're going to start with this table, and in the table, it's always going to have these headings. Categories, we've got either heads or tails. Observed data, we flipped it 20 times and we got 20 heads and 0 tails. The expected data is what you would expect to get if you flipped it 20 times. You'd expect maybe 10 heads, 10 tails. You then take your observed data minus your expected data. So that's 20 minus 10 gives us 10. And here, 0 minus 10 gives us negative 10. You square that value. So 10 squared is 100. Negative 10 squared is 100. You then divide the squared value by your expected values. So here we said that our squared value was 100 and our expected value was 10. So if you take 100 and divide it by 10, you get 10. Here we said our squared value was 100 and our expected value is 10. If you take 100 divided by 10, you get 10. The chi-squared value is the sum of the last column in your table. So the sum of the observed minus expected squared divided by the expected. In this case, the chi-squared value is the sum of the last column, so 10 plus 10 is 20. Now, what if we do a second experiment with a new coin and we get the results that are listed here? Again, we're saying the null hypothesis is that it's purely due to chance, but this time you said, I'm going to use my own coin, not the one you provided. In this case, we observed 11 heads and 9 tails. We expected 10 and 10. So 11 minus 10 is 1, 9 minus 10 is negative 1. Square those values and divide the squared value by the expected value. So 1 divided by 10 is 0.1, and 1 divided by 10 is 0.1. We then add up these values, so our chi-squared value is 0.1 plus 0.1, giving us chi-squared value of 0.2. So what kind of conclusion can you make from the data that you ran in your two experiments with the coins? Which data is legitimately due to chance and which one is not due to chance? Well, in the case of the first coin, the two-headed coin, the chi-squared value is 20. In the case of the second coin, the regular coin, the chi-squared value is 0.2. So the higher the chi-squared value is, the higher the chi-squared value is, the less likely the results are due to chance. And the lower the chi-squared value is, the more likely your results are due to chance. So how low is low enough to say definitively whether the results are due to chance? Well, if your null hypothesis is that you're due to chance and you're attempting to disprove this null hypothesis, How can chi-squared analysis be used to give evidence against that null hypothesis and therefore in support? There's a chart that you can use for that, and the chart is going to incorporate degrees of freedom, which is how much variance you can have in your data and still consider it reliable, and a p-value, which is the probability of the null hypothesis being true. So let's take a look at this. We're going to talk about degrees of freedom first. Degrees of freedom are the number of values in the calculation that are free to change and still get reliable results. So if I give you an example, I say, let's give you 4 numbers. They all have to add up to 100, but one of them must be 50. That gives you 3 remaining numbers that could be a variety of values. Like choice number 1, we have number 50. The number 2 is 30, number 3 is 10, number 4 is 10. If you add these all up, you get 100. A second way to go, you have to keep this number at 50. You can change these numbers and still get 100. You could continue with all these choices. Those are the degrees of freedom. In a chi-squared analysis, it's always going to be the number of options you have minus 1. So the number of options you have minus 1 is the degree of freedom. So in this case, number of categories minus 1. And I just give you some examples here in these bullet points. So what is a p-value? P-value is the probability that the null hypothesis is valid. A high p-value means the null hypothesis is true, and a low p-value means that the probability of it being true is very low. So how low is low enough to say that the null hypothesis is not true? Well, in statistics, they use the confidence interval of 5%, a p-value of 0.05. So this is considered the key p-value to determine what's considered a critical value. The p-value means that if it's less than 0.05, it means it's less than 5% likely that the results are due to chance. If it's greater than 0.05, it means more than 5% likely that the results are due to chance. So here's a table. Didn't come through very clearly on this, but you can Google image this, and you can see that if you're using a two-headed coin, our chi-squared value was 20. The number of options were 2. We had either heads or tails. So degrees of freedom is always the number of options minus 1. So 2 minus 1 gives us 1 degree of freedom. The significant value is always 0.05. So we're going to determine what our critical value is. Looking at the chart, if we go over to the probability of 0.05 and we go down 1 degree of freedom, we get our critical value, which is 3.84. So we're going to compare our calculated value to our critical value. Our calculated value is 20, which is greater than 3.84, which means the probability of the null hypothesis being true is less than 0.05 or 5%. So the relationship is a big chi-squared value means a small probability value that the null hypothesis is true, which means it's not due to chance and you have statistically significant data. So in the two-headed coin, chi-squared value is 20. That gives you a very small probability that it's due to chance, which allows you to say it's not due to chance and is statistically significant. Let's do the same thing with the regular coin. In the regular coin, our chi-squared value was 0.2. Number of options are the same, heads or tails. So degrees of freedom is number of options minus 1. The p-value is always going to be 0.05 for our key p-value. So if we look at our chart and we look at 0.05, 1 degree of freedom, that gives us a critical value of 3.84. Since our calculated value of 0.2 is lower than our critical value, that means our probability of the null hypothesis being true is greater than 0.05. So a small chi-squared value equates to a large probability value, a large probability that the null hypothesis is true. And our null hypothesis is that it was due to chance, which leads to statistically insignificant differences in the data. So 0.2 is a small chi-squared value, which gives you a large p-value, which says it's likely that it's due to chance and is statistically insignificant. So in the two-headed coin, it's pretty simple, right? You say, okay, our expectations are 50-50, but what about a more complex problem? So let's say that I gave an exam and 100 students took my exam, And the different categories would be you could score an A, B, C, D, or F. This is the breakdown of grades by my students. 20 students got an A, 22 got a B, 35 got a C, 23 got a D, and nobody failed it. I expected these values based on previous test results. So let's see if my expectations met my observations for this exam. We're going to find the difference between the observed value and the expected value. So here it's 5, here it's -3, here it's -5, here it's 8, and here it's -5. We're then going to square those values and divide the squared number by the expected value. So the squared number is 25 divided by our expected value of 15 gives us 1.67. And you can continue to carry that out, and to determine your chi-squared value, you simply add up all the numbers in the final column, giving us 11.93. Now, how many degrees of freedom would be in this example? Well, we had A, B, C, D, or F. That's 5 categories, and our number for degrees of freedom is categories minus 1. So 5 minus 1 gives us 4 degrees of freedom. Let's look at the chart. If we go to our probability, the key probability is over here at 0.05, and we go down 4 degrees of freedom, we find that our critical value is 9.49. We calculated 11.93. Our critical value is 9.49. So our chi-squared value is larger than our critical value. What does that tell you about the data? Did the students meet my expectations?